So this is how different way. This is the one of the way that we can manufacture the ICs. Different foundries are available. So each and every foundry, they will try to give the best ICs, with accurate results. So these are all automated equipments will be there. So these are the different chips that are available in a single wafer. Okay. Sometimes it is possible to realize the same chips throughout this IC, or sometimes some chips are meant for different applications. That means various ICs can be manufactured in a single IC. Okay, so it depends on that. It's not necessary that we have to take a same IC for the entire wafer. Different ICs are also they will make. So the final packaging, this is they will take one chip and they will place in a the packaging for the packaging purpose. So different type of packages that are available. So depending upon their depending upon their requirement, request from the customer, they will make those kind of chips and their related packaging they will consider for that. So this is the final cooling purpose. They will use the heat sinks. They will introduce for that one. And then so that is how they will look at whether all the things are manufactured properly or not. Testing also they will do it after the manufacturing. Okay. So actually it's very interesting. It's actually a very interesting thing. You please watch this video whenever you have a time. Okay, I hope you understand this, what the industry will do. So the today's topic is lecture number 7. The CMOS fabrication. Continued. So the last class we have stopped somewhere, and now we are going to do this one. So what we have seen in the last class, where we have stopped. In the last class, we have realized gate oxide. Sorry, what we have seen in the last class. We have well formation we have completed. That is based on diffusion, and then gate oxide what we have formed, and then polycrystalline silicon polygate we have realized. Okay, so these are we have realized in the last class, I hope. Okay, so this is what we have seen. So up to this point we have completed polysilicon gate we have realized. Okay, okay, better I'll consider this. Maybe do one thing. I will write that. Okay, so this is my substrate. Okay, so there I have formed well. So what is this well? It is actually N well we have considered. It is a P substrate. Okay, this is a N well that we have used. I can better use a different color. N well we have used. So this N-well is considered as the substrate for the PMOS transistor. Okay, and on top of it, what we have done, the gate oxide, a very thin oxide, we have formed there on top of it, right? On top of it, we have formed an oxide. On top of it, by using the chemical vapor deposition technique, CVD technique, polycrystalline silicon is formed, right? Okay, fine. So this is what in the last class we have stopped. Okay. So therefore, this is a poly. You have to remember that this is a polysilicon. What is this? This is gate oxide. Gate oxide, or normally we can call it as thin oxide. Thin oxide. Okay, so very important to remember that this is the thin oxide, right? Now the question is that whenever we have realized the transistor, only the transistor gate is available at the middle point. Okay, so at the middle points that are required. Okay, only this point and this point, but other portions are not required, right? So only the portion is required from here to here. The gate oxide and polysilicon is required. Only these portions of the gate oxide and polysilicon is required. Other portions are not required. Therefore, what I have to do, I can remove those portions, okay, by using the etching process. So I can remove the unwanted polysilicon by using the etching process. So it is possible to remove unwanted. Okay, so unwanted poly using etching process. Using etching. Plasma etching normally people will use. By using that one, they will clear that one. Okay, so I'll consider that and put it here. Okay, so I want to remove the unwanted portions of polycrystalline silicon. So with the help of this thing, okay. So not required all these things, okay. Fine. So we can see only polysilicon is at this point. Polysilicon is only available at this point. Okay. Okay. So the gate oxide is not necessary to remove. Okay. The gate oxide is not necessary to remove. So what is the gate oxide? It is simply a silicon dioxide. So okay, let it be keep like that only. Once the thin oxide is completed, then we have to form field oxide as soon as the step is completed. See, the field oxide is whenever we are realizing one particular step or one particular terminal. Once it is completed, we have to cover the entire region with the help of field oxide. That means thick oxide. So that is the usual practice, so that the other portions will not get removed, will not get affected. Okay, so this is how the field oxide that we have to use. It is called field oxide, or I can call it as thick oxide. Thick oxide. Okay, so this is, but what about this one? We can call it as this is thin oxide. So the name itself, so that's depending upon thickness. Okay, so therefore I have covered the entire region with the help of field oxide. Okay, so therefore this the entire thing is related to the field oxide, right? But field oxide is used mainly, the field oxide is used to cover the entire surface, right? That's it. Now the question is that, yes, I have realized the source. I have realized the gate oxide. I have realized the gate. Okay. Now the question is that I need to realize source and drains of a transistor. So I need to realize the source and drain of a transistor. Okay. First of all, I want to realize the source of the NMOS transistor here from here to here and the drain of this transistor. As I mentioned that we have to use the substrate of the N well also because both N material and P materials are N-type material and well also an N-type material. Therefore, substrate is very important for us. So therefore, we have to create one substrate here. So one substrate here. What I can do is that one substrate I need to produce. So the substrate is also required at this portion. I can say that from here to here, I want to realize substrate. Okay. So please remember that here the source is required, drain is required, substrate is required. Why I'm doing these three steps at the same time? Because the same material, N plus material only. Okay. For this, what I have to do. So therefore, the next step is I'll write it here is how many steps have been completed. D. Okay. The E. The next step is E. What are the E step is? The source, comma, drain, and substrate of PMOS. What I can write it here is source and drain of NMOS, comma, substrate of PMOS. Is it clear? So therefore, this is what we have to realize now. Okay. So therefore, I have to consider that diagram again. Okay, copy. And this is the 12 marks question they will give you in the main examination. So therefore, each and every step you have to clearly mention. Okay. So now I have to realize the source and drain. For that one, what I have to do? For that one, actually, once the etching process is completed, I'll do one thing. For better clarity, the field oxide is later on that we have to put it there. So once it is completed, I have to relay the source, drain of NMOS transistor, substrate of PMOS transistor. For that one, what is the first step that I have to follow? First step is field oxidation. Field oxidation. That is what I have to do. What is the second step that I have to follow? Photolithography. Photolithography. So field oxidation and photolithography is all the time, and that means repeatedly we have to use throughout the process, because once the one step is completed, we have to cover the entire region, and once it is covered, and we have to selectively remove some portion for other step. Okay, for that one, photolithography process is used. Okay, now I have to remove the photolithography process. We know that what do you mean by the photolithography process, what steps are involved in this one, all these things we know. Okay, so with that background, I can consider that, you know that. So I will directly remove the unwanted portions of the silicon dioxide. Okay, you please remember that point. Okay. Unwanted portions of silicon dioxide. So these portions not required. Okay, so these portions not required. These portions polycrystalline, the gate, the oxide, silicon dioxide is not required. Oh, sorry. Only this portion, the oxide is not required. Okay, so how I have done this one? By using the photolithography process. After that one, hydrofluoric acid that I have to use it to remove the unwanted portions of silicon dioxide. I hope you understand this one. Okay, so I have opened the window for this one. I have opened the window for this one. I have opened the window for this one. Okay, so therefore, the third step in this one is by using the ion implantation. By using the ion implantation, I can diffuse, I can implant, or I can diffuse the N plus material. Heavily doped N-type materials that I have to introduce in this one. Okay. So pentavalent atoms that I have to introduce within this one. Okay. So that is what I have to do. Copy and then paste it here. So what I have to do is that I have to provide. Of course, I have to remove this one also. Please remember that I should remove this one also, this portion also. So this portion also will get, okay. This portion will get removed very easily, right? So this portion also is get very easily removed since it is also a silicon dioxide, right? But only the thickness is a difference. That's it. Okay. Okay, I can remove this one also. Okay, so after that, I can remove these portions and use the silicon dioxide. Okay, just I can diffuse N plus materials. So it is laterally encroached towards all the directions. In the textbook, they will directly use in this way. E method vaartharu. So just it is not possible to sharp edges. Generally, it is in practically it is not possible. So laterally encroached N plus regions are shown in the given format. Okay, it is N plus. Is it clear? Okay. So that is what important. So whenever we are realizing the source and drain and substrate of the PMOS transistor, it is customary advised to cover the entire other surface, Of course, the field oxide is covered this region, but people will use, they will cover this particular area with the help of mask. So this is the one mask they will use. They will use this mask. So this is called P plus mask. P plus masks. Only this portion should not be get affected. So the entire portion is covered, something like this. Okay, that means whatever we can call, we need to call this is a P plus mask. P plus mask. That means the P regions of the PMOS transistors are masked while we are realizing the NMOS transistor. Okay, P plus mask is required to cover the PMOS transistor while we are realizing the NMOS transistor. Okay, so now similarly, so once it is completed, we have to cover the entire region again with the help of field oxide, and then go for the source and drain of PMOS transistor and substrate of NMOS transistor. Clear? So let us do the same steps again. We have to next F step is next one is now the source drain of PMOS transistor. Okay, and substrate of or bulk of substrate of NMOS transistor. Okay. So to do that one, what we have to do again, we have to do the field oxide. So I have to consider the same diagram again. Okay. So copy and then paste here. Okay. So what we do here in this sense. So I have to cover the entire region with the silicon dioxide. Okay, I have to cover the entire region with silicon dioxide. That means these portions also will be silicon dioxide now. These portions are also silicon dioxide now. This portion also filled with silicon dioxide. Okay, so that means the entire surface again is covered with field oxide. Entire thing is covered with field oxide. Now we have to open the windows. Where we have to open the windows? So again, we have to, as I mentioned that, we have to mention that there is the first step is field oxide. So that is the reason why field oxide and photolithography is a common step. Common steps. Okay. So that means where we have to remove the portions here. The silicon dioxide is we have to remove from here to here and here to here. That means the P plus region for the source and drain of PMOS transistor and the substrate of NMOS transistor. From here to here also I need to remove. Right? That is how we have to do it. So therefore, what I have to do again, I'm going to copy this. Better I have to copy this portion. I think. Yeah, better. No, I'll consider this one. Okay, I'll copy this. Copy and paste it here. Okay, so I want to remove the selectively with the help of photolithography and hydrofluoric solution. Okay, and this portion also get removed. And this portion of certain portion of this one is also must be removed. Okay. Okay. Now this is how the base silicon or open the windows for the required places. So we have to open. We have opened the window for the required portions. So is it clear to all of you so far? Is there any problem? So this portion also not required. Okay, this oxide is also not required. Okay. So just you can imagine that here I have realized somewhat yellow is required. This color I want to use. Here the substrate is we are going to place, source we are going to place here, the drain we are going to place here. Okay. So meanwhile, what we have to do is that whenever we are realizing the PMOS transistor, NMOS transistor must be covered. That means that mask is required for this. Okay. Should remember that point. We have to remember the point that we have to cover this entire region with the help of a mask. But mask is not required at this portion. That means this area must be transparent. The remaining portion must be covered with the glass plate. Okay. Now I'm going to realize by using the ion implantation technique. Okay. So the third step is I have to realize the ion implantation technique. So copy this entire region. Copy and then paste here. So what is the step here? We have to follow. The third step is ion implantation. Okay, so I'm going to realize this is the replace the substrate of NMOS transistor, the source of NMOS transistor, PMOS transistor, the drain of PMOS transistor. Clear? Almost our transistor, the CMOS device is ready. We have realized the source and drain and substrate of one transistor, the source and drain of another transistor also. This is how we can accommodate both NMOS transistor and PMOS transistor in a same substrate. Okay, so the final thing is that we have to go for metallization. Why? Because the metallization is required, because this device must be connected to the external world, right? Some other circuit it must be connected. For that one, metals are required for source, drain, substrate of each and every transistor. Okay, so for that one, what we have to do is that, so what is the final step? This is C. C is metallization. Final step is metallization. So in order to do the metallization, please remember that we have to cover the entire region with again the silicon dioxide. Again, the field oxide is required. So therefore, what is the first step that we have to do? Field oxide again. So field oxide. So that is the reason why we don't want to write the field oxide and the photolithography all the time, because it's not necessary to write all the time. In default, whenever we want to open the window, it is, you should remember that. So there is a requirement of field oxide and photolithography. Okay. So therefore, what I have to do, I can remove these portions. Okay. I want to cover the entire region with the help of field oxide. Okay. So this is the field oxide I want to cover. Okay. So therefore, the entire region is covered with field oxide. Of course, this is also oxide. Gate oxide, field oxide, both are the same materials only. That's the reason why I can cover this other regions also with the field oxide, something like this. Okay, so please remember that why I'm doing like this. But only at the gate point, it is necessary to remember that point. Okay, so in the gate region only, it is very essential to remember that there is a gate oxide. There is a gate oxide. Here also there is a gate oxide. Okay, here we have a polysilicon. Here also we have a polysilicon. Okay, now now we have to open the windows for each and every material, for each and every terminal. Okay, so we have to open the window for this one at this region. Okay, so at this region, I think better we have the black color. So at this region, metal is required. At this region, metal is required. At this region, metal is required. Okay, am I right? This metal is required. Here also metal is required. Here again metal is required. Here again metal is required. Here also again metal is required. How many terminals are there? So this is a 1, 2, 3, 4, 5, 6, 7, 8. Therefore, I have to define a mask consisting of 8 transparent portions must be required. Okay, so in order to remove the selective silicon dioxide, what I have to do again? Photolithography process. There is no doubt at all. Photolithography process that I have to use. Is it clear? So therefore, with the help of photolithography process, I can remove that particular thing. Now, so with the help of photolithography, we have to do that. So I want to copy this one. Copy. I want to paste it here. Okay. So somehow I can say that I can remove these portions with the help of this. The portion is required. A small portion of that is required to remove. So this is a small portion of this one also get removed by using the hydrofluoric acid. A small portion get removed. So here also we have to remove. Here again we should remove. Here also we should remove. Okay, so that is how we can open the window for the substrate of this material, the source of this material, drain of this material, source of this P transistor, gate of this PMOS transistor, drain of this PMOS transistor, and substrate of PMOS transistor. Now I have to fill with metallization. Now I have to go for metallization. So the third step here is that, for the start step, aluminum deposition. That's a better idea. That is how we can write it. Aluminum deposition. So how do we do this one? So take this one, copy, and paste it here. Okay, so therefore I'm going to use this is the technique. Aluminum is deposited here. See, whenever we have aluminum is deposited, so deposition means it will cover the entire region. Okay, so something like this. It will be covered the entire region. It is covered the entire region. It is also covered the entire region. What is happening here in this case? Whenever the aluminum is deposited on all the material, all the circuits, all the terminals, source, drain, gate, substrate, all these are short circuited. Okay, so it is not necessary. So for that one, what I have to do, I have to remove unwanted aluminum on the given surface. Okay, so in order to do that one, what I have to do, by using the etching process only people will use. So by using the etching process, I can remove. So this portion is not required. Okay, this portion is not required. This portion, this portion. Clear? So this is how, by using the so aluminum deposition means we have to use the aluminum atoms on top of the surface. Therefore, that will be covered, that will touch each and every terminal of every material of the transistor. Okay, and we have to remove unwanted aluminum by using the etching process. Okay, so this is the final product for our design, for our circuit. So this is actually, we can call it as substrate of bulk related to the NMOS transistor. Okay, bulk NMOS. This is called the source of NMOS. This is the gate of NMOS, the drain of NMOS, source of PMOS, gate of PMOS, drain of PMOS. This is the bulk of PMOS transistor. Clear? So this is the final product that we have realized. We have fabricated the NMOS device, CMOS device, something like this. Clear to all of you? Is there any doubt? So what is the object in the previous class that we have seen that? Our object is we have to realize the device, something like this. Okay. So this is what we want to realize earlier. Okay. So this objective is fulfilled at this place. So something like this. So it requires these many number of steps actually. It's related to these many number of steps. Okay, so sometimes I'm using the different colors at different places. Please don't bother about it. Okay, so for the sake of simplicity only, I have realized. So for the sake of PMOS transistor, I'm using this one, this color I'm using. Okay, please try to understand the situation. This is also for NMOS, green color that I have used. Okay, so these are the fabrication steps that are involved in making CMOS device. Okay, so this is what actually the fabrication steps related to the NMOS fabrication. Considered as a homework. Realize the P-well process, P-well based CMOS device. P-well based CMOS device. So what we have to do? So instead of NMOS, just I'm giving the just I'm going to give you the this thing. Okay. Just hint I'm going to give. Instead of the PMOS, you have to consider N substrate. Instead of the N well, we have to consider P well. So in a N substrate, we have to consider, you have to change this to P plus, this change to P plus. Okay, and this must be N plus. And it should be N plus, this is N plus, this is P plus, that's all. But the processing steps all are same. Okay, just please remember that whenever we are doing some kind of aluminum deposition, we have to write some statements. What do you mean by the aluminum deposition and all other things? Okay, so photolithography means we have to mention that points also. So this is how we have to realize the CMOS device. Okay, so with this we have come to the end of the session, and we will see the remaining things in the next class. Thank you. If you have any doubt, please send me a Moodle, so you can send me some questions if it is possible. So I will clarify those doubts. Otherwise, you can personally meet me and I will clarify your doubts as well. Okay, this topic here today.